I think we can get started. Welcome back, everyone. So for today's class, we're going to be going back to section 5.4, take a look at those weird 3 different problems that we put down at the end of last class, and then just do a little bit more practice. Part of our goal in section 5.4 is to take a look at the so-called net change theorem. The net change theorem looks like something that's totally new, but it's just a new way to look at the fundamental theorem of calculus part 2. So we'll take a nice quick application in this section. Then once we finish section 5.5 at the end of this week, we're done with chapter 5. Congratulations. All we'll be doing next going forward when we return from the break is taking a look at some quick applications in chapter 6. So we're pretty much just about done, folks. And the applications in chapter 6 are going to be applications for integration. But for us, we're going to treat it mostly as an opportunity to practice integration more than anything. So they're not going to be the worst applications in the world. We might do a couple hard ones in the actual lecture, maybe 1 or 2 in the homework, but there's not going to be any of those nasty ones that are actually in the examinations. The exams are going to be very more about techniques of integration and knowing how to integrate or differentiate the kind of problems we've seen as far as chapter 5 and chapter 6 goes. And then over the break, I'll be posting up a lot of additional information down here, sample exams and things like that. Well, I think that's my full set of announcements so far. Any questions or comments at all, folks, before we get started? Yeah. I'm thinking of doing that probably at the start of our Thanksgiving break, probably say Friday or Saturday. I want to get it kind of done earlier so that it's not any kind of issue over the break if folks want to study early.
Yeah, me too.
I'll make sure to do that. Like I mentioned, I'm intending to put down a couple kinds of review documents. One is going to be a whole bunch of problems, kind of stuff we're used to seeing. Another set of documents are going to be the old final exams in the past that I've given. So that way you'll have a pretty good idea of what to expect, the types of questions, the level of difficulty, the amount of questions, and all that kind of stuff. Any other questions so far? Okay, and just in case I forget to mention this when we come back on Thursday's class, even though we'll have an entire holiday this week, there's no classes, there's no office hours, I think the campus is literally closed. I'm still available. So if you're working, if you have questions, you can still email me. I'll be happy to help out. I'll mostly be checking my email around in the mornings until probably around noon or something like that. But you can email me at any time and I'll just get to all the emails when I get around to checking them in the morning. Well, any other questions or comments at the moment, folks? Okay, well, let's get started. We left, oh, I should open that document. We left some crazy looking problems in there at the end of our work on Thursday's class. If you have the opportunity to take a look at them, let's see if we can figure out just what's going on with them. These all 3 really go together, and like we mentioned before, telling the difference between the 3 of these is really kind of critical and key to understanding the fundamental theorem of calculus part 1, part 2, and understanding what a different indefinite integral is saying versus a definite integral. So as we look at these, let's first say for this one, we're taking a definite integral for sure because we have limits of integration. So let's say here, just to organize our thoughts, this is a definite integral. That we're calculating. And that means we have to find the antiderivative of the integrand. This looks pretty crazy, but it can be done pretty quickly. Did anyone spot what the antiderivative should be? That's correct. Yeah, it just seems odd, but that's the right answer. For this whole function inside here, it's saying the derivative of root x squared minus 1 is your integrand. If you want the antiderivative of it, you just take off the derivative symbol and you're all set. So this turns into root x squared minus 1. That whole thing will be evaluated from 1 to 5. But before we do the evaluation, let's take a look at section 5.3 to just kind of help how we could spot that that's the right antiderivative. In section 5.3, that was up here last week, what we're really looking at is, oh, let's go to part 2. We're looking at the fundamental theorem of calculus part 2. The definite integral of the derivative of f of x is just f of b minus f of a. So that's the whole key to this problem here. Let's copy this in, fundamental theorem of calculus part 2. It's typically written this way, but nothing prevents us from putting a derivative here and expressing it in Leibniz notation. So this right here is the key to that first problem. Let's maybe call this, how are we going to notate this? Let's maybe say this is A, and this is what you need to know for that part A right there. Now let's go back and just evaluate this thing. It's going to turn into a number, and it'll be, for the upper limit, we're throwing 5 inside here. So it's 25 minus 1, giving us a root of 24. Then go minus, then plug the 1 inside here. This will then be the root of 1 minus 1, so it's the square root of 0. So it's pretty much done. If you want to take some extra time, you could factor the 24 as 4 by 6. The square root of 0 is 0, so we're just dropping that term. And if you take the root of 4, you'll get 2 square root 6. So that first one is done right at that step here. Any questions, folks, with that part A? Yeah. It was really by observing this part of the fundamental theorem of calculus part 2. So whatever your function f of x is, for us it was root x squared plus 1, or minus 1. That's what goes here and here, and that's what we calculated right here and right here. So we just immediately throw in that antiderivative. It's weird because it looks one way as a formula, right? But when you actually put in a function, it looks totally different. We have to almost train our eyes to see it right. But does that help out with that part A? Awesome. Other questions so far? Okay, let's take a look at, let's call this, I guess, part B. We'll bring any information that we need, but let's take a look at that again. This is also a definite integral. So this is telling us differentiate your definite integral. Anyone spot what the true answer should be to this problem here? Good call. This one is automatically and exactly 0 each and every time you write down this problem. The reason why is, let's just scroll up to the top for the moment. Every time you calculate a definite integral, you get a number. It's a constant, in other words. So if you differentiate a definite integral, you're differentiating a constant that will always return 0 no matter what. It's the indefinite integrals that give you a true function, and what we typically mean by a true function that can vary. And so if you differentiate something like this, you get a function back. But come down here, even if we took the massive amount of work to find the antiderivative on this thing, this one's not easy at all, but it can be done, you would still differentiate the answer, which is a constant, and get 0 each and every time. So there's really no big formula for this. It's really a concept, and the concept is, since integrate from 1 to 5 root x squared minus 1 dx is constant, its derivative is 0. Any questions so far, folks, on A and B? Okay, let's take a look then at part C. A good call in catching this one. These are really kind of tricky to see because it's notationally dense. The fact that you could see that this one equals 0 just means you've been training yourself looking at this notation and what its meaning is all along the way. So good on that. And one more really notationally dense problem. And you can see what the result should be for this one. This one's really kind of tricky, and it's also kind of a strange problem on its own. Anyone happen to know what theorem we would have to use on this thing? Sorry, say again. It's not the product rule on this one. It wouldn't be the chain rule unless we did something like that. If we change our variable, it becomes a chain rule process. Yeah, go ahead. Exactly. This problem, as crazy as it looks, is the derivative of a definite integral from 1 to x equals, just like you said, change the variable t to an x, and everything else copies in, and then the problem is just immediately done on that stage. Good call. So what made this one work is fundamental theorem of calculus part 1 is what we're really using. And the only reason it's part 1 is because the upper limit of integration varies on that definite integral. So let's just throw this into the notes to connect that thought. And why not? Leibniz notation version is what we use, so we should carry that down too. So part C is really just fundamental theorem of calculus part 2. So here's part C, and here's how we're looking at the derivative of a definite integral. Returns you the integrand, just switch your variable, which was t, or something else potentially, to the x that you see here, and the upper limit up here. So that's the key to getting through part C. Well, we did it, folks. These are not the nicest problems in the world, but I encourage you to come back to these notes. Take a look at these again, because seeing the difference between all three, again, turns out to be really, really important when you're dealing with integration. Any questions at all, folks, with that full set? Okay, congratulations, we've done it. I'm not going to throw a bunch of trick questions like this one on the real final exam. That'd be kind of awful. But again, this is information we just have to be aware of, since it could cause confusion and make other problems a little bit difficult once we get into calculus 2. But let's go down next. I think our notes are just about done. We have the net change theorem. Oh, question first. This one right here. So without Leibniz notation, let me see. It ought to be written as definite integral. Let me get the integrand to be differentiated. It would be root x squared minus 1 would go here. And then playing the role of the d by dx, we could just put a prime right there, and then a dx. Exactly. So this is in, let me say, this is part A in Newton's notation. Oh, yeah, absolutely. Thanks for spotting that. That's a bad way to make an error, just not copy everything in. Yeah, so same exact thing, just a prime here to get it in Newton's notation. Thanks for spotting that. Other questions so far? Okay, I'm glad you asked that question there, because again, these are really, really tricky. We have to know that d by dx could be interchanged with a prime symbol. And now this problem does look totally different, right? But it's the same exact thing. That's part of the challenge with calculus, and it does get a little bit worse the more and more calculus we take, but we expect it. So we just, whenever we see a new symbol, we think about what its exact meaning must be, what the context is, and those kinds of things. Starting out in calculus 1, that's when notation is at its worst because of all the new symbols we see. Other questions so far? Yeah.
So that first one, didn't we do problems like that where you took the antiderivative of the integrand and then plugged in the 5 and 1?
Oh yeah, that would be using the fundamental theorem, and I think it should be, oh, these were all antiderivatives. That would be stuff like what we did right around here on this kind of problem, for example.
So is the only reason you didn't do that because it had the derivative?
Exactly, that's the only reason. So this one, we had to produce an antiderivative, but here, oh, I lost my place. Where do we go? But yeah, just like you said, that derivative here is the only difference between those two problems. Other questions so far? Okay, well, thanks for those questions. I think those were really good questions to ask, the exact questions you would want to ask for this kind of set of problems. And now we have an application problem down below, but you know what? Let's practice with one more problem, and then we'll take a look at that application. Does that sound all right to folks? Okay, so here's the warm-up problem to start out. Let's do a two-part problem. Part A is asking for this integral of, let's make this be sine theta plus sine theta times tangent squared theta. And whole thing is divided by secant squared of theta, d theta. So this one's indefinite. There's no lower limit. There's no upper limit of integration. So we'll find an answer to this, which is going to be a family of functions indexed by that constant C of integration. But another thought on this is we have to do something to get through the problem. A lot of these have to be algebraically manipulated some way, somehow. And if you find yourself in trig functions, not a bad idea to just pull up a browser and put in something like trig identities. These are all over Moodle, but they're all over Google as well. And some of these lists are really kind of excellent the way they format them. So get your favorite list of trigonometric identities, and somewhere there is going to be something that helps us. Let's see. I would probably take a look at stuff like these ones, the Pythagorean identities. And the reason for that is we have tangent squared and secant squared, and they are related this way. Tangent squared theta plus 1 equals secant squared theta. That doesn't help us directly, but it gets us started at least. So now to get to this problem, any volunteers for what this first algebraic step we should take ought to be? Yeah, let's put in our 1 plus tangent squared right here. So we can get down below, secant squared is tangent squared theta plus 1, so that takes care of the denominator, d theta. And now we can do something interesting in the numerator as well. You know, once you see tangent squared theta plus 1, there's also a tangent squared up in the numerator. So if we get rid of the sign, we might be able to do a cancellation. We can't necessarily get rid of it, but we can factor it out. That's the best thing we have available. So let's factor out sine theta. Factoring is division in a certain way. So divide sine theta from the first term, we get a 1. Divide by sine theta here, and it's tangent squared theta. And now at this stage, we have a cancellation. 1 plus tangent squared is the same as tangent squared plus 1. Addition is commutative. You could write that in either order. So it's asking for antiderivative of sine theta. And with whatever we put down, it's a good idea to mentally pause our answers right here and check if it really works out. Antiderivative of sine ought to be negative cosine theta. I'll put in the constant here before checking it so that I don't forget that there has to be a constant. But then let's take a look. If you put in a negative cosine theta, mentally differentiate it. The pen in orange, think of it as mentally differentiation. It'd become negative. Derivative of cosine theta is negative sine theta. And the signs cancel to give us sine theta over here that we're expecting. So that's the end of this process right here. We have infinitely many different antiderivatives, all indexed by choosing a real number C. Any questions at all on that answer down below? Yeah. This one right here?
No, so when you did sine theta and plus tangent squared theta, you have another sign of there.
Yeah, there was sign both here and here.
Yeah.
And if we take a look at this line down below, you could write out sine theta multiplying 1 plus tan squared theta. If we distribute the sign through the product in the parentheses here, it would go here to here for sine theta. And then here to here to get plus sine theta, tan squared theta. So because we factor it out, it essentially just lands in one spot is what kind of happens on this one. That makes sense there? Awesome. Other questions so far? Okay, well, now that we have that, our problem is done. And here's the follow-up question. The next problem says, do the definite integral of lower limit from 0 to the upper limit of pi over 3 of integrand sine theta plus sine theta tangent squared theta divided by secant squared theta d theta. Weird problem in a certain sense, right? It's the same integrand both times, but this is the reason that we like part A, really. Part A is an indefinite integral, and what it provides is the thing we need in the fundamental theorem of calculus part 2. We cannot use part 2 unless we get the antiderivative. And we take the simplest one, negative cosine theta. So these integrals, in a certain sense, they're really related. That's why we're using the same symbol, one with limits of integration, one without. We can come down here and just put in once I get a right pen tool. Negative cosine theta goes in, and we'll evaluate it from 0 to pi over 3. So an antiderivative here provides us a way to use the fundamental theorem of calculus, and we certainly could have just started this whole problem this way. The reason I put down this part A is we're going to find that we do loads of indefinite integrals and not as many definite integrals in this class going forward and in calculus 2. And the main reason is these are still very, very important, but that's the hard step, getting the antiderivative. So a lot of problems, like in the very next section, tend to focus on this step. And then we'll take a look at some definite integrals as well. When we're down here, we still have to evaluate it. And there's a nice trick involved in this. You can keep your negative there. There's no harm in doing it. In fact, let's leave it here once and just show the value in that weird little trick we're about to do. If you leave that negative sign there, unfactored, your answer turns into negative cosine pi over 3. And then this is where it's really easy to get a little bit mixed up with signs, because then it's going to be minus cosine at 0. This minus right here is from the fundamental theorem. There's always a subtraction between your upper limit and your lower limit. And the other negative signs came in because of the negative right there. So either way we do it, we're going to get the right answer. But if we decide to visualize it this way, put an extra parenthesis right here, it's just a little bit more for safety than anything else. Now the negative sign is factored away, and we'll go cosine pi over 3. Here's the minus that we're expecting from the fundamental theorem, part 2. Plug in 0 to get cosine of 0. And this is just a lot simpler to not make a really easy sign mistake. That's the only reason I kind of, if it's just one term, leave the negative sign, or a number like 5 or natural log 3, for example, factored out. At this stage, we just need a really quick trigonometry diagram. Pi over 3 is over here, and its coordinates are going to be 1/2 root 3 over 2. The cosine is going to be the first coordinate, so this turns into negative 1/2 for cosine pi over 3. Cosine at 0 is exactly 1. So this problem keeps on going. This is negative of negative 1/2 after subtraction. And so the whole thing finally settles down at positive 1/2. So that'll be the exact area under this curve here in the integrand. Well, we did it, folks. That's our warm-up question to start us out. Any questions at all on getting through this one? Okay, now let's take a look at the net change theorem finally. When we look at the net change theorem, keep in mind, it's really not doing anything too different than what we've seen already. Like Summer was asking earlier, this is like our trick question part A, but with the prime symbol put in. Let me put that right here just to connect that thought. If we put in a prime symbol, then we're really just doing this evaluation right here. In Leibniz notation, it'd be here with the purple, d by dx. And so now, finally, the net change theorem says, make that just a little bit bigger. If you integrate a rate of change, so here's the derivative in Newton's prime notation, then you just take the net change, f at the upper boundary, f at the lower boundary. So again, it has a fancy name, net change theorem, but this only implies we're doing an application if you see this theorem. It's still the fundamental theorem, part 2. Let's call this, just to emphasize, F for fundamental, T theorem, C calculus, part 2, will be the way how we say fundamental theorem of calculus, part 2, whenever we mention it. So that's our net change theorem, and here's how we're going to use it. This is a problem that we did in section 4.9, where we are given some acceleration of some random particle or some object moving in one dimension. But here we're going to do a little bit more with it. We have acceleration like before. We have an initial velocity, but we don't have an initial position. So there's some missing information. And what we know is this is the acceleration function, and that's the initial velocity for a particle moving along the line. So maybe it's a weird physics experiment. Maybe there's something in a Large Hadron Collider or something like that. This is only going to be valid for 0 to 3 seconds, so a very short experiment. First thing we want is velocity at time t. What we did in section 4.9 is we immediately just formed an antiderivative of this. But now we have slightly more notation. Here's how I would notate it in this section going forward. You don't have to notate this exactly, but it's a good idea to connect the new notation with what we're about to do and write find velocity at time t. That's just v of t we're finding, so set it equal to an antiderivative or in an indefinite integral, or we'll just say integrate acceleration. So all we're doing here, because there's no lower or upper limit, is getting an immediate antiderivative. So we want the antiderivative of 2t plus 3. That's not so bad. For our t first, power goes up to 2, then we divide by 2. So it should just be a t squared this time. For the 3 here, this will turn into a plus 3t. Then just mentally differentiate this. Derivative of t squared is 2t. Derivative of 3t is just a 3. That's the original integrand, so we're definitely in business now. And it's important to mention that this trick here of putting our parenthesis right around that negative sign, factoring out the negative sign, does not work down here. If you have multiple terms, then that's a no-go for us. We just have to take that whole entire result, evaluate it from a lower limit and an upper limit. So I think I got a little bit mixed up on this thing. We're going to take that whole entire result, and I think I need coffee even though it's late, and add an arbitrary constant of integration. For somehow, some way, I forgot it's indefinite halfway through the problem. Does that look all right, folks? Getting back on track? Okay, so once we have that result there, well, we found the velocity at time t, but we have to do a little bit better, right? This is infinitely many different velocity functions. We need the one specific one that satisfies an initial velocity being -4. There's a great trick to this problem. If there's no trig functions or constants here, c is -4. But let's solve it just in case the problem is worse. I would write out for the next step, velocity at 0 equals -4, and that would be in meters per second. Then right over here, where it says of 0, we're plugging 0 into the t variable on this left-hand side. So velocity at 0 means 0 squared plus 3 times 0 plus a constant is -4. And everything just wipes out. It's all because that was an initial velocity at 0. It could have been v at 1 equals -4. Then it would be a 1 plus 3 plus c is 4, and it's an equation with one extra step. But for us, we just get a -4, and so we can say velocity at time t is t squared plus 3t minus 4. So we've got a velocity function. Next thing we'll take a look at is displacement. Any questions first to that stage? Okay, let me show you what we're at really. This is a problem that kind of is trying to connect back to section 5.1. And way back in section 5.1, that already feels like a long time ago, we were in October, we took a look at this problem. Here, the vertical axis is v for velocity. The horizontal axis is t for time. Our velocity curve happened to be always positive. That meant the particle was always moving in the forward direction with however the axis was determined. And we got a distance of 0.82 kilometers. Our problem is a little bit nastier. Our velocity curve is going to go below the x-axis. So let's take a look at it right away before we get too far. T squared plus 3t minus 4. Well, that's not our whole curve. Keep in mind, these should always be given the right domain. So we need to restrict from 0 to 3. So that'll be 0 less than or equal to x less than or equal to 3. And usually that works. Let me see what's wrong here. Oh, I see the problem. It's t for time. That should help a lot. Okay, so that's our whole curve. And that tells us now our curve has some issues here. Right at exactly 1 is where it transitions from being below the x-axis. Here it's moving to the left, up here to being above the x-axis. Here it's moving to the right. And we can find the distance it moved to the right by finding this area, and the distance it moved to the left by finding that area. But what we're really trying to say when we say displacement is, where does it end up after we calculate this whole time interval? So now, if we're calculating displacement, we're taking the negative area and combining it with the positive area to get a net change in area. So that's the net change theorem. It makes a nice show right here, but that's kind of it. The rest of it's the fundamental theorem of calculus, part 2. So think of displacement as net change of the position for the time interval 0 less t, well, these are less than or equals 3. So all we need to do is evaluate. We should call this displacement. I don't have a great symbol for that. Let me just write it out and try to get it to fit. So displacement will be equal to a definite integral. Here we're integrating from 0 to 3. And what we're integrating is velocity, v of t. And just to take another look at that, that's exactly what we were attempting to do in this example here. We're attempting to integrate if we're trying to use an area argument to approximate area. We had an approximate integral of 0.82 in this problem. Here, we can now do it exactly because we just have really, really powerful tools all of a sudden in section 5.4. Let's first start by putting in the function v of t. Integrate from 0 to 3, t squared, plus 3t minus 4 dt. So that's our function to integrate. And this one's not too bad. This takes us back to, say, section 5.3 style of a problem. We'll go term by term and find an antiderivative on each one of those. So it's going to be 1/3 t cubed to start, 3/2 t squared, minus 4t. What I did on every one of those is go to the power of t, increase it by 1, and divide by that brand new power. Then definitely double check it, differentiate that mentally. If we're all satisfied, I'm going to associate the entire thing this time and evaluate it from 0 to 3. This is where I was attempting to make a comment where there's no way to factor out the 1/3 if you have multiple terms. So like this problem over here, we pulled out the negative because that was convenient to us, but no trick like that will work if you get more than one term in your antiderivative. So that was the comment I was attempting to make, just definitely way too early. Sorry about that. From here on out, we just have to calculate this result. Any questions first before we give it a try? Okay, this will turn into 1/3, 3 power 3. All I'm doing is taking the upper limit of 3, plugging it everywhere we see the variable t. Then plus 3/2, 3 squared, minus 4 times 3. And when you're doing a definite integral for this kind of integration, a 0 is like a friend at this point. I would probably not write anything else out from this stage forward because plugging 0 here, here, and here, just nothing but zeros all the way down. But just for the sake of notes, let's do it one more time. It's 1/3 of 0 cubed Control Z is not working. That's a bad sign. Oh, I saved it. That was Control S. Saved it like 5 times. Sorry about that. So I'm going to put in 1/3 times 0 cubed, 3/2 times 0 squared, minus 4 times 0. But then that whole thing is just gone effectively because all of it is 0 altogether. Going forward, 1/3 can factor into 3 cubed, leaving 3 squared. So now that's a 9. This one, let's just take 3 times 3 times 3 and get a 27/2 minus 12. The rest of it's 0. And so this is our answer to calculate right here. Well, let's do it by hand this time. Just to emphasize, you're welcome to do that if you like. If we're doing this by hand, we need a common denominator. So let's start making some changes on this thing. The denominator of 1, we can bump up to a 2. And now that's an 18 to be visualized. This one's all set, but same process on this one. Bump the power to 2, and now the numerator's doubled at 24. And so it looks like we're taking, I'll visualize this as 27 minus 24, so 3 plus 18 to get 21/2 meters. So that's the end of this question on here. Displacement is 21/2 meters, which means, for just an interpretation on this one, after 3 seconds, the particle has a net change in distance of 21/2 meters altogether. In other words, maybe a faster way to say this is the particle is moving to the left and to the right, but at the end of the 3 seconds, it ended up moving 21/2 meters to the right overall. That's what we mean by displacement. We can't actually find the displacement function, which is S of t, because we don't have an initial position. There has to be a S at some time equals some position for us to actually find that function. That's what's weird about this problem. We can still calculate displacement, but we don't even know the original displacement function. And we can go even further. Displacement in this problem is not the same as the actual distance. If this particle was a car, it's not 21/2 meters on the odometer, it's something else. And to do this portion, we really should take a look at the graph to organize our thoughts. Any questions first before we go for the actual distance traveled? Okay, this one's a little bit harder, but if you see these questions in the homework, this would be the place to come back to. We'll go to our graph just to help us out. This one factored nicely, but if a graph is a readily available tool, we'll just use this graph here as opposed to a factorization. So here's our entire graph of the velocity function. Let's just paste it down inside here. And that's way too big. Let's fix this a little bit. So once you have a graph ready, you don't have to post this on your homework, but I would definitely put it somewhere like on Scratch or have it just something to look at on a screen. The next thing I would think of is this. If we look at this area, all of this area here is going to be negative. Area. But if the area is negative, in our current applied problem, that means our particle is moving towards the left, is what the direction is saying. So we're moving to the left. Right exactly here is a time of 1 second. So from 0 to 1 seconds, we're moving towards the left. Then already all the way from here, this one is at 3 seconds. From 1 to 3 seconds, let's use maybe, I guess, green for this. Well, imagine that's a perfectly straight line. All of this area is now positive, so here we're moving towards the right in this case. So let's say here, positive area means moving to the right. So when we calculate displacement, this is what we really did. We found the negative area, we found the positive area, and we just added them together, and the net area was 21/2, but it wasn't the distance traveled. To do that, we need to do 2 integrations now. We need to integrate to find the blue area here, that's distance moving to the left, and then integration of the green area over here, distance moving to the right. The thing we're actually integrating is the function, forgot to put that on there. The function is velocity at time t. So I guess that's the first thing I should scroll up and find. Where did that go? Velocity at time t is right here. You just probably put it here just to make it available. And now let's start 2 more integrations to get through this. I'll start with the positive area. And for the positive area, we have to go from 1 second to 3 seconds. So this is going to be from 1 to 3. We're integrating the velocity function, v of t. And because we're looking for distance, our answer has to come out positive. Now, because we're going from 1 to 3, we're okay. This is guaranteed to be positive area, but we'll have to make a correction when we do 0 to 1 as an integration. So let's get through this one first and see what happens. We're integrating from 1 to 3, the function t squared plus 3t minus 4. But keep in mind, it's not really a new problem, right? We already did the antiderivative. So go to where that was written down and put in the 1/3 t cubed 3/2 t squared minus 4t. And then this whole thing is evaluated from 1 to 3. But again, it's always a good idea with this kind of problem, you don't necessarily have to reinvent some of the calculations we've already done. When we plug 3 into all of this, we got this result. And the whole thing just turned into 21/2. We're going to cite that answer, but let me write it down on paper just to connect that thought. Plug 3 in, and we'll get 1/3, 3 cubed, 3/2, 3 squared, minus 4 times 3. Then we go minus. And now this time we really have to write in the information here because it's not 0. And this is a number we haven't calculated. We'll be careful with this one over here. It'll be 1/3 plus 3/2 minus 4. All I did was plug in 1, and that's the results we will get. Then right over here, instead of putting all this into a calculator or calculated by hand like we did, just cite your prior answer, 21/2. Would go right exactly here. Minus, another thing I want to emphasize, it's not a bad idea to do these by hand. I think it's great practice. It's surprisingly helpful for algebra as well. But if it's getting a little tedious, maybe it's late at night. It is late at night right now. You could plug these into a calculator like Desmos, TI-83, TI-84, even a really, really basic calculator like this will do fractions if you make it. And this one's a little bit tricky. So all I'm going to do for this portion right here is go 1/3 plus 3/2 minus 4. It's a little bit inconvenient. It's negative 2.16667. But if you use a calculator like this one, you can get that in a fraction form really pretty quickly. So a different way to calculate, just to get through the tedium of some of these numbers, which do show up in the homework occasionally. Calculator like this one and many other calculators will allow you to do this. 1/3 plus 3/2 minus 4. Throw that in, then hit the math key, and just immediately hit enter a whole bunch of times. First option is convert to fraction. And that's what we're expecting, negative 13/6. So let's throw that in, 21/2 minus 13/6. If you did give the decimal answer, that would be appropriate too, but I'm trying to go for an exact answer on this one since that's what we're typically going for when it's not an application. So one last thing, 21/2 minus 13/6. Let's convert this to 6 below means we multiply by 3. So this is 63 in the numerator minus 13/6 is going to give us altogether 56 for the area moving to the right, providing none of that arithmetic went awry. Does that look right to folks so far? So I got, oh, right here, oh, that was negative. Then there's an additional negative, so that should be positive. Thanks for spotting that, folks. I was definitely losing that negative sign that time. That's the difficulty with the calculator. I conflated that negative with the negative of the answer right here. That's a bad mistake to make. Thanks for spotting that. So back over here, after correcting the sign, we have 63/6 plus 13 of them. So now we're up to 76/6. The answer just somehow feels a little bit more familiar. I think we've got the right value now. So that's the value that we move to the right in meters. Next, we have to do this all over again. We need to find how far we moved towards the left in meters. So now we're going for the blue area. Any questions first, folks, on getting that 76/6? I think you could, yeah. If we divide by, say, 2 above and below, you're going to be getting, let's see, oh, I was a little bit off, 38 thirds. Yeah, that'd be our simplified answer. 12 and 2/3. And then it could keep on going, right? We could say 12.6 repeating, but either way, we've got a great answer, I'd say. Keep in mind, this one is not the total answer. Our end answer is going to be total distance traveled. So we wouldn't have to take a lot of time simplifying the answer, but any kind of simplification sometimes definitely helps. Other questions so far? Okay, well, if we can do it once, we can definitely do it again, right? Let's do this all over again for the negative area. Well, this one is a little bit tricky, like we mentioned. The distance, this is the problem right here. We want a positive answer when we say distance. Moving to the left is going to be, we'll throw in a negative sign here, integrate from 0 to 1 second. So that's the 0 here where the domain started, up to the 1 second where the velocity transitioned from negative to positive. And putting that negative there is going to force this negative area to now be positive. It's really taking this whole branch of the curve and flipping it over like this to give us positive area in this region. It's in that way we're now definitely getting distance. So let's integrate this next. And maybe just one extra thought here. What we're truly integrating is absolutely kind of nasty. We had to get for distance equals a definite integral from 0 to 3 of the absolute value of velocity at time t dt. That's the actual thing we're getting every time we're trying to get a distance. But if you're integrating an absolute value, you need to find where your function transitions from negative to positive. And when it's negative, put in that extra negative sign to convert to positive. So that's what we're really calculating right here. And then throw in the velocity v of t dt. At this stage, it's lots of copying because we've done a lot of the work already. We know the function velocity at time t, that's this here in black, t squared, plus 3t minus 4. We also know its antiderivative. We've written it down twice. That's this result here in green inside the parentheses. So antiderivative is a third t cubed plus 3/2 t squared minus 4t. The whole thing is associated, and we'll integrate that by evaluating from 0 to 1. So that's our setup so far. But notice we're pretty much done then. We have plugged in 1 and got this number here, which came out as, oh, hang on. There's one mistake there. I've been dropping my negative signs like mad today. Sorry about that. We had a negative sign because we're going for negative distance. That means we can't get too excited by that antiderivative because it involves a negative sign right there as well. So one additional negative sign. Next, we're plugging 1 inside the fraction to get negative. I'm going to associate like this with a big bracket, then plug in a 1 to get 1/3 plus 3/2 minus 4. Next, we're plugging in a 0, but that's the silly one. It's just going to be minus a third times 0 cubed, 3/2 times 0 squared, minus 4 times 0. Then when we do all this work, let's go back up here. We found that this value came out into, oh geez, what did it come out as? Let's see, 1/3 plus 3/2 minus 4. That was negative 13/6 when it was right here. So right over here, that's still negative 13/6. So that means this whole thing is now positive 13/6 altogether once we get to this line. So now we have distance moving to the left, 13/6 meters. The distance moving to the right, that's in green, that was 12 2/3 meters. And our final answer on this is total distance is now, just for the way the distance moving to the left ended up, let's grab this 76.6, just because the denominators are compatible, no other reason. Add to that the 14/6. And finally, the total distance is seen to be, let's see, 89/6. At this stage, again, you can do a lot with this problem, but I think what most people would do, which is a good call, because it's an applied problem, let's just make this rounded to a couple decimal places. 89.6 altogether is about 4.83, or excuse me, 14.83 meters. Then the problem is essentially over here, but we can do one small check just to see if that answer is even reasonable. We did do displacement. Displacement should be less than 14.83 meters. And let's take a look. This was 21.5 meters, which would have been 10.5 altogether. So that actually does fit in the problem. The 10.5 meters from here, let's just fill that in. 10.5 meters is green area plus, or excuse me, subtracting the blue area, keeping the negative sign. Total distance was just adding these areas together without considering this as negative. But we have to throw in that negative sign to force it to be positive. Definite integral regards that as negative area. Well, that's the end of that application there, folks. Any questions at all? I'm getting through this one. Okay, kind of a long problem. It's definitely involved, but it's not terrible in the sense that the antiderivatives aren't so bad. So it's a pretty accessible problem, just with a lot of practice on doing definite integrals. So what we're going to turn to next in section 5.5 is focusing on doing problems like the part A right here. We're trying to produce more antiderivatives, because you might have noticed we don't have a lot of antiderivatives really. There's a lot of stuff we can't calculate. A lot of the problems we've been putting down haven't been too involved. In fact, we've never put down a function times a function really in a lot of these problems. But now when we go to section 5.4, a lot of those methods are now accessible. So let's take a look, excuse me, section 5.5 rather. We just finished 5.4. The substitution rule is finally where we're going to now take a look at how to do more involved antiderivatives. Then we'll see how they combine with the fundamental theorem of calculus. And probably the first comment we should make here is, if you're using a substitution rule, it's because your goal is to invert, or let's say reverse, the chain rule. It turns out this is the first rule that's most easy to do, as opposed to something like the product rule, which is difficult. And we completely ignore the quotient rule. We try to write something that looks like quotient rule as a product and see how to go through it in that way. The trick to the substitution rule is knowing about differentials. So we did this way a while ago, a couple months it feels like. Let's just do this again as a warm-up. If you indicate a y equals g of x as your function, the differential of that function y, like we did in our exam, just goes dy, take the derivative of the function, throw it in, and put in a dx at the end. This reminds us of doing integration, because if you integrate something, you're expecting a dx symbol. So that's how the differential is suddenly getting involved. First, let's take this function here and find its differential. It's w equals tangent inverse of q, as weird as possible. But you would start by taking that w, put it in as a dw. Go to tangent inverse. This one has a derivative that goes 1 over 1 plus your variable squared. The variable is q, so we put in q squared right here. But because it's a differential, there's more to the story. We can't settle with just dw equals all this. We also have to put in one last thing right here. Any volunteers for what the symbol should be in this location? Good call. If the variable is q, we should put in dq right here. So that's the full differential. And finally, here's what it does for us. In the substitution rule, you're going to have this kind of setup in your integral. There'll be a function, say your f of x. It'll involve an inner function and the derivative of the inner function. Each and every time we did the chain rule, that's how the result always came out. The function, we threw in the inner function, unadulterated, just copied it in, and then we multiplied by the derivative of that inner function. That's the result of a chain rule. So this is saying undo all that. Well, all you have to do is take your u, that's going to be the g of x function right here. That's the substitution in this rule. That's why it's called the substitution rule. We substitute it out, calculate its differential altogether. The differential would be g prime of x dx. But that means g prime of x dx right here is completely replaced with du. And instead of f of g of x, we just say f of u, because u is that g of x function right inside. So that's the process, but seeing the process is one thing, doing it is a whole nother. So let's practice a bunch of these before we run out of time, and when we come back, we'll practice a whole heck of a lot more. Any questions first before we start out? Okay, this rule is not as bad as it seems, but it's one of those rules which kind of makes or breaks Calculus 2. Without really great knowledge of the substitution rule, we're in dire straits in Calculus 2. We have to figure it out and get going, because Calculus 2 doesn't start here. It starts with integration by parts, undoing the product rule. And it's assuming we're already pretty fluent with this when you're getting started. So that's what makes Calculus 2 really tough. There's no real break between the two classes. So let's start off with a nice friendly problem to get us started. It's going to be new set of notes here. For part A, let's integrate 1 plus 3x minus 7x squared multiplied by 3 minus 14x dx. So if this is our problem, there is a couple ways to do this really. You could just multiply out the whole thing, and that would absolutely work. Oh, I forgot one thing. There's a power 5 there, so you can still multiply this all out, but it's just going to be really, really rough. You're going to have lots and lots of terms and integrate every single one of those terms. That'll be your answer, but that would take way, way too much time to do. So instead of doing all that, we're looking for an inner function. Anyone spot an inner function in all of this stuff here? Exactly, it's inner to the power 5 function. So I would think of this as the inner function, and let's let that be our u. Set u equals 1 plus 3x minus 7x squared. So that's our start on this one. And the thing that's kind of rough about the substitution rule is this is not a guarantee that it's going to work. The substitution rule is one of those kinds of problems where I think our author says something along the lines of, it takes a little bit of art, and a little bit of trial and error, and persistence. It's natural to guess wrong on your differential and just keep on trying again. So even if this is wrong, I'd probably still leave it on the paper and try a different u. But I think we're in good shape here because notice that the derivative of this thing right here looks an awful lot like 3 minus 14x. We're on the right track if that's what we're seeing. So our step 1 is write down the u that's in the substitution. Our step 2 in this problem is we have to calculate the differential. That's an important enough step. Let's write it out. Next, calculate the differential of u. So we'll do it immediately right down below. Du will go like this. Du equals we're going to have multiple terms. So like we mentioned way back when we were doing differentials the first time, we do need parentheses. Derivative of a 1 will go to 0. Derivative of 3x will be a 3. And then for the last term, we'll get a negative 14x. And because it's a differential, we have to put in a dx to match the variable that we were differentiating on. So we have our whole differential here. And step 3 is to make the substitutions. So we go back to our original problem. And we'll start putting down just a couple colors just to color code things and show where everything is going to go. That right here, that's our u function. Here, that is the right-hand side of the differential, including the dx right here in the problem. So we can say that this whole thing is going to turn into antiderivative of u to the power 5 to start. So we've made a substitution right here in the substitution rule. And now, for this whole thing, 3 minus 14x dx, this is an algebraic form, we're going to swap out a du immediately and just throw it in right here. So here's du. So we took something which was the result of the chain rule and wrote it down in this way. The function f is just the power 5 function written this way. F of u is, well, there's the u inside, and we're multiplying by du as well. What we really are trying to do with the substitution rule is transform an integral that looks horrendous, there it is, that's a pretty terrible one to get through, into something that we're familiar with and should not be more than a couple steps to get through. So our step 3 is to make the substitutions. The next steps are just to finalize our answer. So we can call the results here just our step 4. We need an antiderivative of u power 5. Well, that's excellent, right? All that happens is we keep the base u, power goes up, so now it's power 6. Divide by 6, so it's 1/6 in front. And here's the step I forget awful lot. Don't forget the arbitrary constant of integration because it's still just an indefinite integral. The answer is now a family of different functions, all differing by this constant. But it's still not done, unfortunately. Anyone see what the last steps should be? Yeah, good call. Even in ordinary algebra, if you're solving something by substitution, you have to undo that substitution when you're getting to your final answer. And the idea here is, if the problem started with dx in your integral, the answer has to end as x. So I would say step 5 is a pretty critical step as well. We must undo the substitution and return to the original variable. And this is where I think yellow highlighting is good. When we say original variable, we're meaning the dx right here. But that's pretty fast. All we're going to use is what we said u was and plug it in right where u is right here. So the final and last answer to this whole thing goes equals 1/6 of, throw in u, it's 1 plus 3x minus 7x squared. We can close off that parenthesis and put in power 6 now, plus a constant. And that means we've done it, folks. We have done the chain rule, but this is going backwards in a very, very literal sense. This is really the backwards process of the chain rule. It's weird to learn a rule like that forward and backwards, and it's odd that the chain rule is the easier one to do. But once you get to that result, I would still do one last thing. This one is optional, and it's something you could do mentally if you'd like. Scratch paper is a good idea as well. Let's say 6 for step 6, which is optional. I would definitely do this, especially if I have extra time, say during an exam. It's not a bad idea to check these out and just see if they work. Take your whole answer, 1/6, 1 plus 3x minus 7x squared to power 6, plus that constant, and just differentiate it. So now we're really just doing a check. If you differentiate this thing, you are definitely using the chain rule. 6 is the outer function, so we differentiate that first. 6 comes down and wipes out that 1/6, and now the new power is 5. Then the thing we copy in here will be the 1 plus 3x minus 7x squared. Then the chain rule says immediately multiply by the derivative of this inner function right here. So over to the right, it's going to be 3 minus 14x. And double checking, that really is our original integrand. So we managed to find the correct antiderivative to that bizarre looking function up here. Any questions at all, folks, on that conclusion here? Okay, well, we have 2 whole minutes so far. That's not a lot of time to do another problem. Sorry about that. I was hoping to do at least a couple more, but the problem we just got through before these notes was definitely a long one. When we come back on Thursday, my goal is to just practice a lot more of these. On my notes, if we scroll through here, we're going to do a lot of antiderivatives, but then we'll combine it with the fundamental theorem and show how can we now integrate with the fundamental theorem and ask your problems where we need the substitution rule. And I might leave these questions down below for just extra information. We might not get that far in the notes. I'll double check these aren't in the exercises, but I doubt they are. But they're pretty cool ways to integrate things where you know you have even or odd functions. So if we have time, we'll try to get to these. But if we don't, I'm going to make sure they're not actually on the homework. Well, have a great night, folks. If you have more questions, I'll be available down below. Otherwise, drive safe, and I'll see you all on Thursday. Thursday's going to be the hard one right before the break, but I'll definitely be here. Thanks.
Yeah. Second,
Sure.
was to actually, am I doing this correctly, or do I have to bring it e to the x?
Let me grab a thing to point with. So you've got that right antiderivative here, but once you get to this step, you wouldn't have those symbols. You would just put a bracket that goes around.
Yeah, I
And go
noticed
-5
that.
to upper
It's just,
5.
I put myself in the habit of doing that, but no, is
Gotcha.
that okay though?
And then once you go to this step, 5, -5, yeah, that looks great.
Okay, okay.
That looks awesome.
Second question.
Mhm.
What's the point of the du?
The du right here,
Yeah,
the du is just going to be the new symbol that goes right here. So
right,
if you have a variable of u, there has to be some symbol to say what you're integrating with.
okay,
Like up here where you had the x's, there had to be an x for the dx to say integrate with respect to x.
okay,
So if we change the variable to u, we have to throw in the du. And that's why we are using this du here.
okay,
So think of that whole thing, dx just swaps to du.
okay. Weird, okay.
Yeah, it's very weird,
And so
actually.
then why doesn't it get transferred down and just,
Well, after you get the antiderivative, that's like what I was mentioning over here, oh, that other problem over here. Once you get the antiderivative, dx does go away.
okay,
So on your problem, you throw in a bracket and go from -5 to +5.
right,
But on this one, once you get the antiderivative, we just put in the constant.
weird, okay.
Make sense, kind of?
Kinda, yeah. a little bit.
Gotcha.
I'll look at it later.
Okay,
I just have.
sure.
How did you get, so from the notes, how did you get U6?
Oh, so when you're doing the antiderivative of this, the power
Yeah.
always goes up by 1. And
Because
just
is
to,
it 5 plus 1? It's like.
Yeah,
n
exactly.
Plus 1?
yeah,
Oh,
let me show you
okay.
the formula that we're using for that one. It's gonna be in, I think this one's in 5-4. And the rule is this one right here.
Oh, okay, because I was a little lost.
Sorry
Okay.
about that.
So I add n plus 1, so 5 plus 1, and I get 6. And that's how we got 1, 6,
Exactly.
2, right?
So that's the +1 here and the +1 here, exactly.
Okay, yeah, that's what, okay, that makes a lot more sense now.
Cool, glad to hear
Okay,
that.
thank you.
You bet. Any questions, Jake?
I don't understand 5.1.
Well, that's when we're doing like the areas of stuff,
Mhm.
right? Like these kind of problems here.
Yeah, I was looking at this and I didn't see how I'm supposed to solve it.
Well, the first step you do is this right here. Find out how many rectangles and then do this equation.
So basically the b minus a.
Yeah, exactly.
Amount of rectangles divided by the map.
Exactly, yeah.
And BA would be one.
So it would be, let's actually look at your question there. In this problem, the B was 30 and the A was 0, so it's just the bounds for the function.
Basically, good,
Yeah, exactly.
but we don't have that on the thing, we have it as a graph.
Let's take a look at that. So this is assignment 11 up here, 5-1. Oh, what problem is this one? Number 3, gotcha. I keep having the wrong thing. That's the answer. Let me try something more helpful for us. Okay, 5.1 exercises. Let me close these before we have too many of them. It says estimate the area under the graph of 1 over x. So the 2 here is going to be your B, the upper bound.
And the one's gonna be A, so it's gonna be
Exactly.
2 minus 1.
Yeah, exactly.
Who's gonna write that down because might forget that later. 1, and then N, and now how do I find N?
Let's see. It's right here where they said the 4 approximating rectangles. So that's your n value.
N 4, which is gonna be 1/4.
Yep, now you're looking at 1/4. And these problems, a fraction 1/4 is okay, but sometimes it's just as convenient or more convenient to call it a 0.25. So whatever makes the most sense to you, fractions or decimals.
All right, so I probably might change it to decimal, because if it's solid numbers, decimals work better with that, but fractions work better with fractions.
Sure, yeah, exactly. Just kind of just depends on how it looks when you're putting the problem together. Just go for the most convenient format.
And then what do I do after that?
So after you've done that, we've got to, it's 1 over x.
And that must be X then.
The first x value is going to be this 1 right here.
So 1 over 1 would be 1,
So your first value is going to be 1 to start.
and then the next one's gonna be 1/2,
Our,
because it's gonna be 1 over 2.
would really be at 1.25 altogether.
Okay,
You're going from 1 to the next by adding your delta x, which is 1/4, or I guess I went for fraction 0.25. So you get all your x values, or sorry, but no, that's x1, the next one over.
okay, so every point I go off, I keep adding the 1/4.
Yeah, exactly.
Okay, so the next one would be technically 1.5,
Exactly.
and then it would be 1.75, and then 1, 2, and then, well, you just keep going.
Well, remember it said use 4 rectangles.
Oh, you just
So
keep
stop
going
here.
until you reach the rectangle.
Exactly.
Then you reach
So the,
2.
you end right at there. Yeah, if everything is going according to plan, that's how it should go each time.
1 equals 1. 1 equal. And then what I do after that?
So I'll show you what it looks like visually, but then we'll look at the formula.
Yeah.
Oh, geez, I lost it. Hang on. So visually, what we're doing is that we're actually looking at the rectangles, and the way we calculate it, it's gonna be something like this. So in your problem, it's gonna go delta x,
So 1/4,
f that, x1, x2, x3,
and X4.
exactly. So this is your last thing to calculate. And like you said, the first one, I think you said. 1/4,
Basically,
right?
just all of those plus together times the delta.
Exactly. And the reason it works is this distributes through, right?
So if I just put those into, so I distribute.
Or you don't have to. This is more for visualization.
So I can technically just put the parentheses and put this into a calculator and technically.
Yeah, exactly.
Okay, and then that would probably be, then that would be the final answer.
It would be, yeah.
And that final answer technically, because all of that got together. Need. $7.5 together. Times 1/4.
How'd you get that? 7.5.
Added all those together.
Oh, but it's not those values you're adding, it's the function at those values. And your function is one over X in the problem. Let me double check
So
actually.
technically would be the base value, so it'd be 1/1.
Yeah.
And 1/1.25 and 1/1.5.
Much more annoying as a calculation, but yeah, that's what it turns into.
Okay, so it's just more tedious then, so.
Yeah,
it would-
because you're using this function f of x.
It would just look like this,
Yep, you're on the right track.
and it'll just keep going,
Yeah, once you have those four terms, just throw them in a calculator, you've got your.
and it would be the same on for 4 and 5.
Let me check first. So this one was estimate using 4 approximating rectangles and right endpoints. But this one's at left endpoints.
Mhm.
So if it's at left endpoints, we change the formula to, coming on this one,
That one too, that one,
is 4 rectangles again. So let me put here, this is at right endpoints with 4 rectangles. Left endpoints with 4 rectangles goes,
negative,
well, be a delta x to start. And then these are the right endpoints. The left endpoints go f at x naught, f at x1, f at x2, f at x3, that's all 4, and so that's a calculation here for left endpoints.
so. The right starts at the 1, and the left starts at the 0.
Yeah, you could think of it like this, right endpoints, you're using all of these, you're using the rightmost. Left endpoints, you're using these, you're using the leftmost.
Basically, left means you just start from the beginning, the right means you just move over one and keep going.
Yeah, exactly, that works on each one of them.
So if it said left of 2, you would go 0 and 1, and then you got it. Because it's just 1 and 2.
Yeah,
It sounds, it would be confusing if you had to do both side by side, and then you convince. Swap the two,
yeah,
but it doesn't actually sound that is actually quick.
you know, that's a good question, actually, and people do that. They do the lower endpoint rule, the upper endpoint rule, average their answers, and that's now a better estimate. And that whole process is now called the trapezoid rule. So if you average your left endpoints and your right endpoints, you're not looking at rectangles, you're approximating by trapezoids now. Weird stuff. Absolutely, yeah.
Technically, you really think about it, math is technically go on obvious because people try to